Hi, my name is Owen Redwood. Welcome to the Offensive Computer Security course lecture on fuzzing and automated testing for vulnerabilities. This material is hosted at hackallthethings.com. This is a good quote that's going to be a theme of this lecture, is that any sufficiently advanced bug is indistinguishable from a feature. And we're going to dive more into that in a little bit. First, we're going to cover bugs and the differences between vulnerabilities. We're going to go into the nuances about effective testing versus ineffective testing. We're going to dive into fuzzing, the fundamentals from high level down to low level mechanics. We're going to cover computer science theory, limitations of testing. Then we're going to dive into how to design a test harness and the important details there, what values to fuzz and how, what targets you should hit, how to analyze crashes once your fuzzing is successful, and then extra topics including some hands-on with AFL and code coverage tools. At very, very high level, there are two types of testing. There's general testing, which encompasses regression testing, developer-written test cases, unit testing, and testing based on the specification. And then there's random testing, which is the topic of this lecture, and is meant for stress testing features or perhaps problem areas of the program. And in my experience, fuzzing finds more bugs that are more interesting than all other forms of testing. So there are a lot of challenges to testing. How do you verify that software performed correctly given an arbitrary test case? Is it giving a integer output, or is it timing based, or is it graphical in nature? Depending on what it is, this may not be ascertainable from a test that's automatable. Furthermore, determining any side effects is another challenge, and this requires insight and intuition into the challenge areas on the developers of the specification in order to predict these problems, in order for the devs to test for them. And it's another problem if you can't distinguish bugs from features. If it's something that seems like a bug but appears to be in the specs, maybe it's baked into the specs or standard. That is an entirely different challenge in itself. Next, if the bug symptoms are so subtle that they evade automated testing or even manual testing, is testing useless? Now, some may say that the notorious heartbeat bleed bug would be an example of this, because it's information leak. If you send it the right packet, it's going to reveal some contents of memory, which isn't the same as a crash, not the same as a DOS, not the same as any other bug, but the information was leaking was actually contents of memory revealing passwords or keys, degrading the crypto system effectively. And it is actually an example that could be caused by manual testing if you use the right compiler flags, but I digress. There are many other bugs and vulnerabilities out there like this one. Hopefully, prior to the testing, you have some well-documented code or written specs that involve details for what they would like to be tested. And maybe they had some test cases to give to your unit tests that they developed during development. In other words, TDD, testing-driven development. However, in almost every case, these are totally insufficient because developers are not aware of security problems. And they've specifically, or at least the supervisor specifically explained the testing expectations. And at least the criteria for success. But in reality, all companies, even despite the testing, ship software that contain bugs and contain vulnerabilities. And most testing is to ensure that features are working as intended and are not actually concerned with security. And then when testing is concerned, There's a big debate over whether it's more important to find a large quantity of bugs or finding very quality bugs, and how to reward or incentivize developers depending on how your priorities are. Well, depending on whether or not your priority is the latter, and how to judge that. Um, and the last bitter fact on this slide is that although testing is appreciated when it makes sure features are operating properly and the bugs are squashed out there, it's not ever going to be appreciated for the sake of security unless there's a major failure. And in that case, everyone's going to be chewed out. And you're not going to be able to say in your defense, but what about all these other vulnerabilities we prevented? Because I doubt the boss would care. Um, you'll always have bugs that you just can't reproduce. And this is from a book by James A. Whitaker titled Exploratory Software Testing. And it is a honest to earth job advertisement that we should be seeing for testers, but you would never see in reality. Software tester wanted. Position requires comparing an insanely complicated, poorly documented product to a non-existent or woefully incomplete specification. Help from original developers will be given grudgingly. Product will be used in environments that vary wildly with multiple users, multiple platforms, multiple languages, and other requirements yet unknown but just as important. We're not quite sure how to define them, but security and performance are paramount, and post-release failures are unacceptable and could cause us to go out of business. Unfortunately, job ads don't read like this. They just say minimum years of experience with these languages, and etc., and certifications. And, well, that's about enough of that depressing material. Let's get on to the meat of the topic and get into the technical content. So there are three primary methods for discovering vulnerabilities. We've covered source code auditing in C and C++. We've covered reverse engineering for x86, and we're going to cover fuzzing in this lecture. There are lots of tools out there for source code auditing, including compiler flags and source code auditing tools. For reverse engineering, there's a handful of tools, including debuggers and stuff like that, disassemblers like IDA, Binary Ninja, and others. But you have to have a good deal of skill in order to perform this task. Fuzzing is easy. Lots of tools and frameworks exist for it. It's easy to make custom ones, and whether or not you have the source code is unimportant. You at least have to have the means to run it dynamically and do dynamic testing. There are other methods that you should keep in mind. These aren't the authoritative only three ways to find vulnerabilities. Includes symbolic execution, some static analysis techniques, dynamic testing with dynamic taint analysis, and other data flow testing. And ultimately, these all find bugs, but not all bugs are vulnerabilities. In fact, the minority of bugs are actually vulnerabilities. And it's the point of fuzzing is really to narrow it down and find the exploitable bugs, because those are a priority. Fuzzing is, the definition is the repeated process of sending specific data to the application in the hope to elicit certain responses. So most people define it as random testing. It's better done as specific. There are infinite ways to fuzz something wrong under the realm of purely random. Sending specific intelligent input to the application under test is the smarter way to do things. Now, the certain responses primarily involve crashes or other forms of easy to catch errors. Anomalous behavior is very difficult to find, and finding invalid application state transitions is a bit more difficult as well. It requires some editing usually of the application source or infrastructure. Now, fuzzing is used very effectively for bug hunting, but also inside basically every major software organization and company in their software testing and their secure development lifecycle. This is important to Google, Microsoft, Apple, Mozilla, all the top corporations that put out browsers, operating systems, virtual machines. Um, Not so much on phones yet. Nowhere in embedded systems, as far as I can tell. But still, the big contenders in the market that care about security care about fuzzing because it's superior testing over human-driven testing. So there are 5 general phases for fuzzing. First, you identify the inputs of the application, in other words, the attack surface that you would like to fuzz. You then figure out a strategy and execute it to generate fuzz data and test it. You then execute the fuzz data, which involves looking for the exceptions, errors, and crashes in the application under test. So you have to have some form of debugger or test harness monitoring the target. And finally, once you get crashes, you determine the exploitability of them. And we have more slides on each of these throughout the lecture. So, mutational fuzzing is one of the top level strategies for fuzzing, and it basically involves taking a body of sample inputs that are hopefully well formed and pretty diverse, corrupting them in a algorithmic manner, and then iteratively testing the application with each new mutation. Now, the output of a mutational fuzzing strategy is only as good as the mutator and the inputs. This fuzzing strategy can't figure out new inputs unless it gets lucky. And it is strictly limited to the features captured by the sample body of inputs, or the seed files, otherwise known as a corpus. So, if you have a poor corpus that has low entropy in terms of the possible feature set that could be captured by all of the possible corpuses or input files for the application, you probably won't cover really interesting code paths. The next strategy at a high level is generational fuzzing, or model-based fuzzing. This is also sometimes considered grammar-based fuzzing, but that's a lower level mechanic that I'm going to dive into in a bit. This basically involves a model that is capable of building the data based on a model that is constructed by the Fuzzers author. It could be simple, it could be really smart, or it could be random. And it can be, if done right, highly efficient. The best starting points for this type of approach are any open source projects that are compatible with the target you wish to fuzz, perhaps for speaking the protocol, for generating the files, or generating whatever inputs may be used to interact with the target, and also exploring the specification. If it has an RFC entry, going there and finding out what edge cases might be worthwhile to fuzz, especially if they seem especially interesting or complex. But as I said previously, there are infinite ways to fuzz something wrong, and so the only drawback with this approach is the limit of your understanding of the inputs and constraints of the program that you're trying to fuzz. So, as I said, the RFC and any other specifications are very useful for pushing past these barriers, so you can develop your fuzzing accordingly. And that being said, it's very, very hard to generate complex protocols. Like a simple case would be cloning kittens, and a more complex case would be cloning variants of human beings or Homo sapiens. And then the third high-level approach is differential fuzzing, and that encompasses any approach that actively reduces the testing state space, which often explodes in other approaches and makes the cost of exhausting it very hard. So this focuses on test case reduction, focuses on efficiently covering code paths and code coverage, is something we're going to talk about in a little bit. And so it involves sometimes constraint recognition if there's instrumentation done on the binary, as well as the use of heuristics to make these decisions to refine the fuzzing. This would be an example of how fuzzing state space would be refined. This is from AFL-Fuzzer, and they're fuzzing the gzip binary. The first round exhaustively goes through these test cases. It's noted that these selected ones that are chosen for stage 2 actually cause the binary to do something different when it's tested, and so it keeps iterating at each stage, making those observations. Now for lower level mechanics, at each round or throughout the fuzzing process, the fuzzer may employ techniques that are considered to be oblivious, to be block-based, grammar-based, template-based, heuristic-based, and or instrumentation-based. Oblivious-based mechanics is essentially just random fuzzing, piping from dev random into the input, or mutating it with just purely random. There's zero consideration for progress code coverage, what may solve the constraints better, or anything if it is done in this way. You can still use random mutation in a smart manner, but if you do it without any consideration for these, this is considered oblivious or blind. Block-based mechanics is drilling down the accepted atomic level inputs for the program down to blocks. They may be delimiters, they may be tags. For markup language, they may be protocol, keywords, and etc. And the fuzzer may select from a library or catalog of these blocks or meta characters, perhaps, when generating the inputs to throw at the target. Grammar-based mechanics are very important to understand. If you've taken any computer science class or artificial intelligence class that delved into things like Prolog or other languages like that, this is fairly straightforward then. Otherwise, it's a custom grammar. There's no standardized one to generate the format. It may be something like header, body, footer, and for each three of these keywords, various things will match to it once the grammar is parsed, and the output would be randomized, well formatted output for the fuzz testing. It makes it elegant to describe the test cases, and there's an example here that was released this year, the Dharma Fuzzer. If you would like to read an article, this summarizes it quite nicely. Template-based mechanics is very similar to block-based. You have templates for the given test case or file format you want to explore, and it could be a set of packets you want to send before each test case to get the application to the right state. It could be a specific file format, header, or packet frame, or media frame, and etc. This is obviously the template-based approach is for exploring specific code paths. Heuristic-based mechanics is any mechanic that involves making smarter decisions on how to trim the test state space or to reduce the number of test cases or to evaluate code coverage and fuzz accordingly to maximize code coverage. And or to dynamically build correctly formatted inputs in case it recognizes there is repeated failure. All of these kind of are on the same side of the coin as differential fuzzing. Finally, there are instrumentation or introspection-based mechanics. This is an essential part of the testing process. It's one of the core components of the test harness. There's various levels that instrumentation could happen at. It could be by running the process and then attaching a debugger to it, or running it through a debugger, running it through some sort of tracing a debugger, doing binary instrumentation, which requires having the source code, or doing intermediate language, which usually requires source code, but for x86 there's tools like Mixema, which can lift raw x86 assembly up to an intermediate language, which can allow symbolic execution like analysis, but also can provide other forms of fuzzing instrumentation for especially constraint recognition. Now for an important number that anyone who's constructing a fuzzer or planning a fuzzing campaign should be aware of is the Eddington number. It is 1.57 times 10 to the 79, which is approximately 10 to the 80. And scientifically, it is the theoretical number of observable protons in the universe. That's perhaps discounting dark matter ones if they have a dark matter analog. So this is important for space complexity. If you try to generate and store over 10 to the 80 test cases, you will likely fail. But if you try to iterate through 10 to the 80 test cases, that's fine. That's also bordering on the realm of cryptanalysis in terms of whether or not this is feasible. The feasibility is dictated by whether or not you have an algorithm to determine success in your iteration. Mainly for fuzzing, that is generating something that can crash the application under test. So, for some examples, an Ethernet frame, which your computer is using right now to talk to the internet to view this video, or to have downloaded it. It is 1500 bytes by default on most ISP carriers, which with 8 bits per byte renders it at a state space of 2 to the 12,000, which is far greater than 10 to the 80, I assure you. So it would be infeasible to generate all the possible packets with which you could fuzz an Ethernet level application service or router appliance. Similarly, for an HD picture, you have 1920 by 1080 pixels, and each one of those pixels is represented by a nice HTML-friendly hex triplet. If you just have each pixel represented only 3 bytes, one for the red, green, and blue values, the whole state space for fuzzing every single color across every single pixel and every combination thereof would be approximately 16 million to the 1920 by 1080, which would be far more than 10 to the 80. So the point is, it's not always feasible to exhaustively test or fuzz applications. There will always be bugs because of this for any sufficiently large program. Therefore, targeted approaches in fuzzing is paramount in order to do it effectively. Another complexity issue is time. Fuzzing, however, is often parallelizable. Therefore, doing cloud-based or distributed-based fuzzing is huge optimization. And if your fuzzer is doing its task in generating, testing, and evaluating on a big O notation of O to the n to the x, some exponential cost, you're probably doing it wrong when it is usually, in most cases, just the cost of the input generation. So to recap, before we go any further, there's 3 high-level paradigms: mutational, generational, or model-based, and finally differential-based fuzzing approaches, which may employ any combination of lower-level mechanics which span across block-based, template-based, the use of grammars, heuristics, obviously the use of introspection and instrumentation to determine whether or not there's uh, unusual behavior or crashes occurring. Which brings us to how to determine that. Because fuzzing things without paying attention to them is a total waste of time. So crashes are the easiest thing to detect in a fuzz test. Usually you can do this with a debugger on any platform that comes with the operating system or the hardware itself. However, in software, detecting subtle or nuanced behavior like logic flaws or side effects is very, very hard to detect. Uh, for the general case, it is infeasible, and according to Rice's theorem, any non-trivial property of a function, it's kind of infeasible to have an algorithm that computes whether or not that property is actually manifest. So, for detecting crashes, there are multiple approaches. You can check if the process has died, if you're able to attach to it. If you can't, you can check if the PID is gone. You can check if the process is zombified. You can check the logs. But for, say, black box testing, where all you have is like a piece of hardware, uh, hopefully you have multiple copies because you're probably going to break it doing something like this. Just honestly putting in a clamp, right? Um, but if you can't lift the binaries off of it and emulate it and get it working in any form, uh, then how can you even detect crashes? How can you debug it? Um, this test case or a scenario is much more difficult. It, on the other hand, is the subject of my dissertation, which we'll be talking about more at Hack All the Things, but I digress. Hopefully, you have some means to observe the state of the application under test while testing it, and can observe very discrete events like a application crash, at the very least. So, homework 5 of this class is probably better to be called Project 5, the only project, is worth 10% of the grade or so, and the goal is to fuzz an existing program to find a zero-day vulnerability and to ethically disclose the bug to the vendor. It has been done in the past with great success, and the students get to put a CVE on their resume, and they talk about it in every interview they have. It's a great enabler of their career success, and it's a incredibly succinct milestone to prove your aptitude and security that you can communicate vulnerabilities that you have found and you have proven to be vulnerable. So let's cover some guidance I can give on fuzzing. Um, First and foremost, all fuzz input that's generated must be common enough to pass the elementary checks in the application. So if the application is expecting 9 inputs, if you only give it 8, then you're not passing a basic constraint and is going to exit on you before executing 99% of the application's code. But at the same rate, the application, you have to explore its uncommon code paths. And you want to trigger some exceptional behavior like a crash. So it's got to be common but also uncommon enough to trigger this sort of behavior. Now, just like a toy example, this is checking if x is greater than unsigned int 10. If so, it performs some dangerous code. Otherwise, it skips this branch and keeps going and performs some safe code. And determining how to generate this is a source of a lot of computer science and computer security theory, ranging from constraint solving to symbolic execution, and so on. And and while not every constraint has dangerous code behind it, it is essential that your fuzzer is able to access, or at least explore and test and stress test the risky areas of code. So here's another example. Testing terminology would denote this as two different paths that this branch could take, or this statement could take, and sometimes there may be multiple ways to satisfy any given constraint. There's ands, ors, etc. As I said earlier, this is a basic example, checking whether or not there is the proper amount of input to the application. However, the constraints in general get more challenging. Determining how to solve for x for the general case of any complex type is infeasible, and it's generally attractive, or code paths are generally more attractive when they perform more complex operations than simpler code paths. However, according to many publications, there is no correlation between code complexity and code vulnerability, which, strangely enough, is, I guess, reality. And there's other ways that data can be handled in complex manners. There's bit packing strategies, which correlating that to multiple constraints is difficult, especially if the granularity of your constraint solver doesn't go down to the bit level, but only to the byte level. So, in general, types of things that are worth fuzzing for local applications, and the goal of privilege escalation going in through environment variables is perhaps worth exploring. For general file fuzzing or protocols, positional arguments, flags, bits, header metadata, and stuff like that. Other delimiters and formats within file formats, like media has audio, video, and perhaps other things embedded inside of it, captions and different languages, perhaps network protocols. There's a lot of aspects here, and web apps. For network protocols, fuzzing the beginning, ending parts of a protocol or a handshake. Fuzzing any deep states for state transitions and stuff like that if it's a stateful protocol. And if you're testing, say, a CMS like WordPress or plugins or something like that, testing it with multiple users, seeing if you can privilege escalation or access things that only the admin should be able to do, be able to inject scripts to test cross-site scripting, and other meta characters, which we'll get to later in this class. So the goals are ultimately to see if you can, at the very least, DOS the target. Ideally, you want remote code execution, so that involves exploiting a memory corruption vulnerability or some script injection vulnerability, and being able to inject or manipulate the target to execute malicious code or malicious computations, which is the latter case in reference to ROP, which we'll cover at the end. So we've covered, obviously, integer overflow and underflow wraparound problems, the difference between signedness and unsignedness, and how that matters for bounds checks. And when you're testing integer values, it depends on what the variable or the constraint you're evaluating is. If it's a byte, the range is 0 to 255 for unsigned, negative 128 to 127 for signed. Similarly for short, it is all listed here. So These serve as a nice reference for shooting directly to the border edge cases. Um, Fuzzing with exactly a set, including 0, 127, 255, 655, 35, 32767, and etc. going upwards, hits all the edge cases for all the integer data types or numerical data types in terms of their bit width, and allows you to play around with any wraparound cases. And I actually found a vulnerability like this once, hunting for a integer wraparound. The developers implemented their own malloc library to replace the standard C implementation, and in malloc they have a case that checks for the +1, where if it was the max size of that value and they were doing +1 to have perhaps account for a new line or something like that, it would then wrap around to 0, so they check for the 0th case. Now I found the developer actually later on using +2 for some reason later in the code, which meant if you got it to the max value and wrapped it all the way around, it would pass this test, malloc a chunk of size 1, but then still try to write a max value amount of data to it. Very easy to exploit, because it was also involving function pointers. This is an old slide. Basically, you can divide the max 32, max 16, max 64, max 8 just by 2, 3, 4, and then play around with plus or minus 1 or 2 bytes, 16, 8, 32, etc. And string repetitions are another easy case. Simply increasing by order of magnitude will be sufficient to catch any string-based buffer overflow. But sometimes in CTS they have built-in checks to make sure you're not throwing A's at it. So checking out different characters actually also makes a difference in other anti-reverse engineering checks, as well as sometimes on the heap. But more interesting than that, these cases, delimiters make things go wrong more often. So all of these special symbols you could think of are a delimiter in some language or another. And just recently, a pretty long-standing, must have been a decade or two, vulnerability was found in Linux in the libUzzer code, which is the library used to change passwords and update users' information and passwords. And it allowed the arbitrary change of any user's password given access to a single account, which is an extremely serious priv-esque vulnerability. Format strings, which we've covered already. Fuzzing simply for %s and %n have the greatest chance to trigger a fault that you can detect with the fuzzer. And you should fuzz very long sequences. Character translations and character encodings are also extremely important nowadays. And depending on the character set in use, there may be character modifiers and that account for super accents and sub accents, and obviously fuzzing across languages is a good idea, as we all learn from the famous iPhone crash SMS message list displayed here. It made it on all the news channels, and we talked about it earlier. So, for instance, with UTF-16, there's a way to pack multiple accents per character, both above and below it. I think /xcd packs it below and cc packs it above. And so you can pack this arbitrarily deep in some cases. They don't have to line up as the same. Here's a better reference on it. So This is especially useful in any web application exploitation because they have to handle multiple character sets and typically accept multi-byte characters. So in the second byte, or the least significant byte, um, or whichever byte is not used to display the character but instead accents, you can pack uh, SQL, cross JavaScript, ActionScript, and other escape characters and syntax characters that enable exploitation. Uh, and this Etherpad link contains a rather extensive reference of all the possible multi-byte characters that we've found so far that end with escapes. And it's in the Appendix C that a lot of them are listed, and multiple character sets from Japanese to Korean to Chinese to etc. And for directory traversal, dot dot forward slash and dot dot backslash are important to try depending on whether or not the system is Unix or Windows land. And this is useful when targeting web apps, network daemons, etc. and might reveal remote file inclusion or file access vulnerabilities. And it's important to try different character encodings. And that brings us to the overall category of metacharacter injection, or rather syntax characters. Ampersand may be a single syntax character, but two side by side may represent something very unique in that language as syntax, which is why two of them I would consider a metacharacter. And a metacharacter is anything that triggers the interpreter or the application to start processing the input data in a different manner. Perhaps you now treat it as a script or a command or a different form of data. But I digress. We will revisit this later during the web application exploitation lectures. File types are another interesting aspect of fuzz. You can spoof magic numbers in Unix. You can spoof file extensions in Windows and Linux. And there's ways to play with content metadata and web traffic in the post fields. And another interesting aspect is opening files for Microsoft Office products in special folders opens them with special permissions and can allow privilege escalation. And it doesn't require that users permissions to put those files in that folder. If I recall correctly, there's special folders in Windows that it just treats with priority. This is another thing that I've suggested over the years, but I haven't seen any fruit in fuzzing it. Having a file that is recognized as multiple files validly. The following proof of concept is a valid portable executable, PDF, HTML, plus working JavaScript, and a jar with a Python file embedded in it, which is pretty interesting. It's kind of a Pandora proof of concept. And well, going back, I guess my insight on it is it might be useful for fuzzing things like a network security appliance on the network that's scanning packets, downloading files, and doing malware analysis on them. It may not be able to reach the right conclusions. Anyways, more towards networking. Modeling arbitrary network protocols is very difficult, especially when the protocol is not known. And the protocol may be tunneled under another protocol over SSH, and it's possible to tunnel something over DNS. And with Scapy, you could pretty much arbitrarily tunnel anything within anything that it allows. So that might be an interesting way to fuzz an application. Also, bit flipping known protocol headers and flags is another useful way to fuzz protocols. Also, putting them in weird time states with NTP. If it's a crypto service or SSH server or some other server, it may be an interesting way to mess with it. But if you truly do not know the target protocol, you're mostly out of luck. But this is not so uncommon. Reverse engineering botnets and botnet traffic usually involves very customized protocols that didn't go through much engineering review, but it was just one guy hacking in his basement trying to figure out how to get his botnet all to talk together, so it's got to have some weaknesses. But this is a topic that is a large focus of my colleague's class, Joshua Lawrence, and his offensive network security courseware that he is developing. He's taught it previously last year and is going to get around to recording videos for it and hosting the courseware at Hack All the Things. So, if you've gone through all of this, you've fuzzed your application for a while, you've walked away from your computer, you've slept a couple days, and you come back and you've got some interesting crashes, how do you analyze them and differentiate from the bugs and the actual vulnerabilities? That is the purpose of the rest of these slides. So there's three main steps. You want to replay the input to confirm that it is a crash. You want to then do a root cause investigation to find out what code it is crashing in, and then finally determine if it is exploitable. So replaying and fuzz testing is absolutely essential. Your fuzzer, if you didn't design it, may have bugs in it itself. Some crashes may be false positives. They may be artifacts caused by bugs within the fuzzer itself. So the one way to determine if it is actually a crash is to get it to repeat over and over. Once or twice is typically sufficient. And repeatable crashes are the good cases that you want to look at for determining whether or not there is an exploitable vulnerability. So here's the second most important thing, root cause analysis. Having a bunch of repeatable crashes and dumping them on a developer's bug tracker without doing root cause analysis, is a surefire way to get banned from the bug tracker. Some of my students, despite my suggestion they not do this, actually did this, and I got several angry emails from the VLC devs saying that they're going to ban everyone from @fsu.edu, and I apologize. So I have put some slides together on this. What you want to do for crashes is compare the stack base backtrace at the point of the crash. This should be given to you by the debugger that is spitting out information of your fuzzer. This is if you're coding a debugger from scratch, almost every guide should instruct you how to do this. It's relatively simple. Now, if the symbol information is stripped out, or if it is otherwise not available at the time of the crash, then it may require stepping through with a debugger to find out more information about the neighborhood of the code that it's crashing in, at least at the function level. You don't need to go down to the line within the function. But you absolutely need to go to at least this level. Because if you find multiple crashes that all crash from the same function, you only need to report one. You don't need to report a ticket for every single one. That is how you get banned from a bug tracker. You can submit multiple crash files for the same ticket. That is the way to do it. So this is really, I can't emphasize, this is incredibly valuable to do this analysis. Finally, determining whether or not the crash you are looking at is exploitable is a topic that we cover across over 5 lectures later on in this class. So the thing you want to do first and foremost is disable the system exploit mitigations and security mechanisms that are enabled that would make this process hard. Most notably, address space layout randomization, ASLR, as well as NX and DEP, stack cookies if you have the source and can recompile it without those, are useful to disable at this point because it allows you to go about with ease to hijack the instruction pointer if it is hijackable and proceed in landing a really simple payload. All you want to do is land a debugger interrupt, which is in x86 the opcode CC. It's a trap instruction. If you don't disable these, you're going to waste a lot of time trying to land any, especially with the ASLR, land anything to a stack-based payload or otherwise. Um, so, for more on this, just stay tuned. This is a topic to very much be continued. So, that brings us to the final topics of this lecture with some demo videos. First, AFL, which stands for American Fuzzy Lop, has a weird name, but it's a great fuzzer. It's a differential fuzzer that requires source for the target because it uses compiler flags to do binary instrumentation so that at the end of every round of fuzzing, it goes and analyzes which test cases cause the underlying branches to choose or decide different branches to maximize code coverage. So, AFL provides two C and C++ compilers, respectively GCC and Clang, and then G++ and Clang++, to provide this fuzzing instrumentation so that it can trim the sample fuzzing inputs based on how well they're exploring the code paths instrumented in the binary. And this can be done on a per library basis. It doesn't have to be for the master binary if you want to target deeper libraries, such as the case in like a media player if you're targeting a specific codec. The way you would do that would be to rebuild the library or the target binary with the AFL compiler, and if it has a auto reconf or autoconf and auto make process, and there's a .configure stage, the way to easily do that is at the environment. This is a one-liner that will do it. You simply tell it which C compiler and C++ compiler to use by providing these environmental variables for the context of this given command, which will be ./configure. And it will just go ahead compiling it with these new, with the AFL compilers, which will add in the binary instrumentation. I've had some trouble with it in fuzzing very large binaries. It also does not allow inputs over 1 megabyte in file size, which is a second problem. Now, there's a way to get multiple AFL instances to work together, and the way to do that is to have a single master instance, which is the minus capital M, and you give it a name, and set up the rest of the inputs corpus and the output result file, and what the binary, the application under test is, and any parameters it may have, and then the slaves that work with the master all are designated with -s, and each have to have a unique name. It may complain at first about the CPU frequency not being optimized for the fuzzing, and it will abort. The way to tell it to ignore that warning and to continue anyways is a AFL option that is AFL skip CPU freak equals 1, and then you put that before AFL fuzz itself. This is what a screenshot of AFL will look like while it's running. Within the terminal, you may have to expand the size of the terminal for it to display properly, but it goes over the runtime, the time it's ran since the last unique crash, so it does crash minimization to detect if a group of crashes are actually the same vulnerability or bug. It also does hang detection, and one of the AFL settings is the timeout timer to wait for each test. If an executable goes past that timer, it's considered a hang. I think the default is 3 seconds, which may not be long enough in many contexts, so that is something that must be set. And so it goes over also the number of uh, fuzzing cycles that have gone through, and it describes here the current stage. There's Havoc, Interest, Trim, and a bunch of others. Each do separate things. Havoc is the random mutator. Trim is the stage that analyzes the progress of the current cycle, determines which fuzzing inputs performed best, and then trims the fuzzing inputs set based on that result to optimize the next cycle. In that regard, it is the component that makes it differential. And the exec speed and total execs are basically your rate and your progress bar. There's no upper limit for total execs that one should shoot for, or minimum bar that one should shoot for in order to consider something sufficiently fuzzed, as each application will wildly vary, also based on a number of factors, including what inputs you're testing it with. Now, the exec speed, you want to get it up as high as possible, so doing anything you can in the setup of the fuzzer to optimize this number and crank it up is going to have a massive reward in terms of any effort you put in this department. Here it goes over what fuzzing strategies have yielded what results. Here is the total cycle count, total paths encountered in the binary, and unique crashes and hangs detected. This is a kind of a code coverage metric, and these two kind of cover that. The favored pass is something that is detected by the the instrumentation to lead to either let me put it this way: a code path at the very beginning that checks if it has the correct number of inputs, and then proceeds with the rest of the execution of the application would be a favored code path. The abort branch for that would obviously be not a favored code path. And the code geometry gives you a feeling for the topology of the target binary and the complexity that each cycle has to cover. And if you ever have to pause a AFL campaign, it is essential that you pass it the right command, the right parameter when you resume it. Otherwise, it'll restart all of your progress and erase what you've done so far. And so it is -I space minus. I don't know why it is that. I forget. It's in the help documents for it, but that specifically instructs it not to overwrite progress. It is safe, I think, to have that in from the get-go. So there are a lot of ways to fine-tune things. Obviously, I've covered the timeout to make sure you're not just detecting a hang every time. Address Sanitizer will slow down the execution of the binary, but it is very useful in C and C++ binaries for detecting all sorts of heap-based vulnerabilities, buffer overflows, and etc. And the compiler flag in GCC and G++, as well as Clang and Clang++, is -fsanitized equals address. It is something that came out of Google, Address Sanitizer, and has been implemented as a standard compiler option in modern compilers. And the AFL compilers are versions that support this. And you have to tell AFL to use Address Sanitizer in its instrumentation, otherwise it will cause problems. Now, I've had problems using 64-bit version of ASAN with AFL, and so I recommend if you're going to use address sanitizer, do not do it on large binaries. If it's a large binary and you're targeting just a shared library like a codec, then it might be doable. And in such a case, try to target the 32-bit version because that I've had less buggy results. It detects crashes when there aren't. It will fail to detect crashes in cases that they are. Like I can pass it a file that definitely causes a seg fault when I open it normally, but it fails completely when it's in AFL and using ASAN to detect it on large binaries that are 64-bit binaries. And so another good resource is a bunch of tips listed in the AFL master documents, which is linked here. If you have been running AFL for a long time and not finding bugs on a big target, it may be due to a number of problems I've already discussed, but you may want to ask yourself, are you targeting linked libraries, and if so, are they instrumented with AFL? You can apt-get the source, rebuild them to have other parameters like ASAN on, as well as you'll need to rebuild them with AFL's compilers. Secondly, try reducing other instrumentation and security measures. ASAN, or address sanitizer, may cause problems on 64-bit systems, and other instrumentation flags may as well. And this is outlined in the AFL's documentation. And AFL, I've found, has problems catching crashes that occur in shared memory. So if you are trying to test it with a file that definitely causes a seg fault, but it occurs in some shared memory region, then that may be the reason why AFL is not behaving properly. And finally, make sure to double check your your configure flags and see the documents for any notes on your target binary and what you're trying to instrument it with. There are a couple blog posts that are worth mentioning here at the end. Speeding up the fuzz speed is something that's been documented here, and using AFL instead of a file fuzzing format for fuzzing instead a server with a protocol is a good read and described here. There are several other good fuzzers worth mentioning. Perhaps the most popular would be Peach Fuzzer. There's also BFF and FOE out of CERT. There's libFuzzer, Grinder, which is Windows-based browser fuzzing. There's a Linux system call fuzzer from nowhere.net. There's many web fuzzers. There's a PHP Vuln Hunting 1.2. And this is a blog article that's worth reading from Trail of Bits. It's about the DARPA Cyber Grand Challenge, which is a competition to automate fuzzing, landing of exploits, and patching of vulnerabilities, and much, much more. And their write-up on how they designed their fuzzer and their vulnerability discovery platform is a very interesting piece, totally worth reading. And the Embedded in Academia blog here also is on fuzzing. It's a good read too. And we're going to cover more next time. These are other good papers worth reading. There's the rocket-propelled chainsaw. There's differential testing for software, adaptive random testing papers if you're interested. And we will have a bonus video on AFL and LCOV for demo videos demonstrating how to use these tools and these techniques. Till next time.